Welcome to this video lecture. I am Dr. A. Uma Devi, Associate Professor of Mathematics with Vanyaperumal College for Women, Perumal. I am going to give a short lecture on measurable sets. First of all, I let you know about what is a measure. It is a non-negative extended real valued function defined on collection of sets of real numbers. That is, let M be a collection of sets of real numbers. A set function M that assigns to each set E in some collection M of sets of real numbers a non-negative extended real number M of E called the measure of the set E, which has the following properties. Measure of a set is defined for each set E, which is a subset of capital M of real numbers. For an interval I, measure of I is nothing but its length. If sequence En is a sequence of disjoint sets of measurable sets, then measure of union of En is nothing but sum of the measures of the individual sets En. Now, we are going to prove that every Cantor set has measure 0. To prove this, first we are going to construct the Cantor set, and next we are going to prove that the set is measurable, and finally we are going to say that the measure it has the measure 0. First we construct the Cantor set as follows. Consider the closed interval 0, 1. The first step in the construction of the Cantor set is to subdivide this closed interval 0, 1 into 3 intervals of equal length 1 by 3. That is, you divide this closed interval 0, 1 as closed interval 0, 1 by 3, open interval 1 by 3, 2 by 3, and the closed interval 2 by 3, 1. Each subinterval is of length 1 by 3. Now, you remove the middle open interval 1 by 3, 2 by 3 from the interval closed interval 0, 1 to obtain the closed set C1, which is nothing but the union of the closed interval 0, 1 by 3 and the closed interval 2 by 3, 1. Now, you repeat this open middle one-third removal on each of the two intervals in C1 to obtain a closed set C2. That is, you subdivide the closed interval 0, 1 by 3 as closed interval 0, 1 by 9 and open interval 1 by 9, 2 by 9 and the closed interval 2 by 9, 1 by 3, and you remove the middle open interval 1 by 9, 2 by 9. Similarly, you divide the closed interval 2 by 3, 1 as the closed interval 2 by 3, 7 by 9 and the open interval 7 by 9, 8 by 9 and the closed interval 8 by 9, 1. You remove the middle open interval 7 by 9, 8 by 9. Then we obtain the set closed set C2, which is the union of 4 closed intervals, each of length 1 by 9. That is, C2 is written as the union of these 4 closed intervals. Next, we now repeat this process of open middle one-third removal on each of the 4 intervals in C2 to obtain a closed interval C3, which is nothing but the union of 8 closed intervals, each of length 1 by 9. We continue this removal operation countably many times to obtain a countable collection of sets CK. Now, the Cantor set. We define the Cantor set C as intersection of these closed intervals CK, which is countable intersection. Therefore, K varies from 1 to infinity. That is, Cantor set is nothing but the points that remain as K tends to infinity, and that makes up the Cantor set. Now, each CK is closed. We know that arbitrary intersection of closed sets is closed. Therefore, C is a closed set. Also, the set C is an intersection of a countable collection of closed sets. Therefore, C is a Borel set. We know that every Borel set is measurable. Therefore, C is measurable. Hence, we have proved that the Cantor set is a measurable set. Now, we are going to find its measure. C1, C2, etc. They are all disjoint union of closed intervals. Therefore, measure of C1 is nothing but measure of the closed interval 0, 1 by 3 and the closed interval 2 by 3, 1 Measure of an interval is nothing but its length. Therefore, since each interval is of length 1 by 3, measure of C1 is 2 by 3. Similarly, measure of C2 is nothing but measure of these 4 closed intervals, each of length 1 by 9. Therefore, measure of C2 is 2 by 3, the whole square. Continuing this process, Ck is the disjoint union of 2 power k intervals, each of length 1 by 3 the whole power k. Therefore, measure of Ck is 2 by 3 the whole power k. Now we know that if A is contained in B, then measure of A will be less than or equal to measure of B. Here, C is contained in Ck for all k. Therefore, measure of C less than or equal to measure of Ck for all k. As 2 by 3 is less than 1, 2 by 3 the whole power k tends to 0 as k tends to infinity. Therefore, measure of C is less than or equal to 0. As measure cannot be negative, measure of C is equal to 0. This implies the Cantor set has measure 0. Hence, we have proved that every Cantor set has measure 0. I hope you all have enjoyed this lecture. Thank you.